Now we continue to learn Chapter 5, Orthogonality. Section 2, Orthogonal Subspaces. And Part 1, Orthogonal Subspaces and Orthogonal Complement. First, we see the definition. Two spaces X and Y of Rn are said to be orthogonal if X transpose Y equals 0 for every X in capital X in this set and every Y in the set Y. If the sets X and Y are orthogonal, we write X orthogonal to Y. Use this notation here. See this example. Let X be the subspace of R3 spanned by E1, the first coordinate vector, using the standard basis. Okay, and let Y be the subspace spanned by E2. If X belongs to this set capital X and Y belong to the set Y, then these vectors must be of this form. So X in this form, X1, and the second and the third coordinates are 0. And Y, only the second component, Y2, and other components are 0. Okay, thus we have X transpose Y equals X1 times 0 plus 0 times Y2 plus 0 times 0 equals 0. Therefore, X and Y, these two sets, are orthogonal. Now we need to mention that the concept of orthogonal subspaces does not always agree with our intuitive idea of perpendicularity. Okay, so here, see this figure. We may feel this space, this plane, and this plane, like they are perpendicular to each other. However, we should see these two planes, they are not orthogonal subspaces because XOY plane, you can find this vector in this plane, 1, 1, 0, this vector in XOY plane. And for YOZ plane, you can find another vector X2 equals 0, 1, 1. And if you do the scalar product of X1 and X2, it is 0 times 1 plus 1 times 1 plus 1 times 0 equals 1, which is not 0, okay? So, the XY plane and the YZ plane are not orthogonal subspaces, although you may intuitively think they are perpendicular to each other. They are not orthogonal. Okay. Now we see this example. Let X be the subspace of R3 spanned by E1 and E2. Let Y be the subspace spanned by E3. If X belongs to this set and Y belongs to the set Y, then you can have X transpose Y, this scalar product, equals X1 times 0 plus X2 times 0 plus 0 times Y3 equals 0. So for any vector X, any vector Y in the two sets, their scalar product equals 0. Thus, we know that this set, this subspace X is orthogonal to the subspace Y. Furthermore, X is a set of all vectors in R3 that are orthogonal to every vector in Y. So here you can see from the figure. So X is a subspace of R3 spanned by this coordinate vector E1 and this coordinate vector E2. And E3 is just this coordinate vector. It spans a one-dimensional subspace of R3. And these two subspaces, they are orthogonal. And also X, this subspace, contains all the vectors that are orthogonal to every vector Y, every vector in Y. So this example gives us another concept. We call it orthogonal complement. Okay. Let Y be a subspace of Rn the set of all vectors in Rn that are orthogonal to every vector in Y will be noted by Y orthogonal complement. That is, Y orthogonal complement contains all the vector x in Rn such that x transpose Y equals 0 for every Y in this subspace Y. The set Y orthogonal complement, we call it orthogonal complement of Y. So what does this mean? So this means Y orthogonal complement contains all the vectors that are orthogonal to this subspace Y. And also any vector that is orthogonal to every vector Y in this subspace must contain in Y orthogonal complement. So Y's orthogonal complement should be the largest set, right? Contains all the vector x that are orthogonal for every vector Y in this given subspace Y. Note, the subspace says x equals span of E1 and y equals span of E2 of R3. Given in example 1, they are orthogonal because every vector in this subspace and every vector in the latter subspace, if you do the scalar product, is 0. Okay. However, they are not orthogonal complements. The orthogonal complement of x should be span of E2 and E3. And the orthogonal complement of y orthogonal complement equals the span of E1 and E3. So this is the largest set that contains all the vectors that are orthogonal to any vector in X. Okay. Similarly, this set is the largest set that contains all the vector that is orthogonal to every vector in this subspace Y. Now we have some remarks. Okay, if X and Y are orthogonal subspaces of Rn, then X intersect with Y is the zero vector. Okay, and second conclusion is that if Y is a subspace of Rn, then Y orthogonal complement is also a subspace of Rn. We can see the proof. The first one, let X belong to X intersect with Y. Because X and Y, they are orthogonal subspaces, so we know that length of X power 2 just equals X transpose X. Because X in subspace X and X also in subspace of Y, and they are orthogonal, so by the definition it equals 0. So X transpose X equals 0. This implies X cannot be any other vector but the zero vector, can only be this zero vector. Okay, now we consider the proof for the second statement. If X belongs to Y orthogonal complement and alpha is a scalar, then for any Y in the set in the subspace Y, we have this one, alpha X transpose times Y equals alpha times X transpose Y equals alpha times 0 equals 0. This implies alpha X also belongs to Y orthogonal complement. If X1 and X2 are elements of Y orthogonal complement, now we consider the addition. Okay, so X1 plus X2 transpose Y equals X1 transpose Y plus X2 transpose Y equals 0 plus 0 equals 0. So this indicates that X1 plus X2 also in Y orthogonal complement. Therefore, Y orthogonal complement is a subspace of Rn, because we show that for scalar multiplication and addition, the two operations are closed in Y orthogonal complement. And also, of course, Y orthogonal complement is non-zero, is not an empty set. Okay, so this is a subspace of Rn. Now, let us denote the range of A by Ra. So, the range of A equals all the vector B belongs to Rm, where B equals A times X for some X belongs to Rn. which is also the column space of A. And the column space of A transpose, Ra transpose, is a subspace of Rn. Okay, so Ra transpose contains all the vector y in Rn, because if A is a m by n matrix, then A transpose is a n by m matrix. Okay, because A transpose is a n by m matrix, this column space Ra transpose should be a subspace of Rn. So it contains y belong to Rn such that y equals A transpose times x for some x belongs to Rm. So they are in different dimensions, right? The range of A should be a subspace of Rm, while the range of A transpose should be a subspace of Rn.